I'm not going to imagine that you've never seen the x-axis and the y-axis and plotted points and talked about the quadrants and that sort of thing before. That's done in previous classes that are prerequisites for this class. However, in the spirit of trying to make this as self-contained as possible, I'll say a little bit about how we look at the connection between an ordered pair of real numbers and a point in the xy plane or Cartesian coordinate system. And what I generally do in courses where students have less previous experience with that sort of thing is I begin with an equation like x plus 2y equals 8, x plus 2y equals 8, and then open the floor to suggestions on a value of x and a value of y that we can put together, substitute into this equation at the same time, and make it true. Basically, a solution to an equation in two variables is an ordered pair, an x and a y, of real numbers that when you substitute the x for x and the y for y, it makes it true. So what's one ordered pair that satisfies this equation? 0, x equals 0, y equals 4. If we check it, 0 plus 2 times 4, 0 plus 8 equals 8. So that works nicely. I will indicate that as an ordered pair, 0, comma 4. And then we look for others. What's another x and y that go together make this true? 4, 2, x equals 4, y equals 2. 4 plus 2 times 2, 4 plus 4 equals 8. So that makes it true. 4, 2. 2 or 3 more. 8, 0. 8, 0. 8 plus 2 times 0, 8 plus 0 equals 8. So 0, 4, and 8, 0 are kind of the nice ones where one of the coordinates is 0. It makes the other coordinate easy to find. Those points are going to be on the axes. We'll call those intercepts. There was another one? 2 and 6. 6 for y might put us a little bit too big. X would need to be negative in that case, which was not a problem. What if we let 6 go for x? What could y be to make it true? Y equals 1. 6 plus 2 times 1, 6 plus 2 equals 8. That would work. And I probably need another even number for x because y has an even coefficient. There's an even constant on the right-hand side. So how about x equals 2? What y value would fit with x equals 2? 3 work. 2 plus 2 times 3, 2 plus 6 equals 8. So 2, 3. I think these are the only 5 ordered pairs, both of whose coordinates are whole numbers, to satisfy this equation. If we allow x or y maybe to be negative, we get lots more solutions. If we allow x or y to be non-integer rational numbers, fractions, decimals, that sort of thing, we get a lot more solutions. If we allow x or y to be irrational numbers, we get ridiculously more solutions. But these are the only 5 where both the coordinates are whole numbers. What I want to do, there's no way to list all the solutions to this equation, but we can draw a picture of them. So I want to draw a picture of them. Now, if we want to do this to keep track of them, we need 2 copies of the real number line. We need a copy of the real number line to keep track of the x values, and that is what's traditionally known as the x-axis. We draw a horizontal copy right there. I'll just extend it a little bit, indicating the positive direction is to the right. There's a 0 point on there somewhere, and we need to select a scale, 1, 2, 3, 4, 5, and so on. So this is to keep track of the x values. Perpendicular to that, and intersecting at the 0 point for both of them, we need a second copy of the real number line to keep track of the y values. We call this the y-axis, of course, and by convention, its positive direction is upward, and we indicate a scale on there, 1, 2, 3, 4, and so on. So this would be the second copy to keep track of the y coordinates. Now, if there's a correspondence, if there's a particular x value that corresponds with a particular y value, like 0 corresponds to 4, then we would want a single point where we could recognize that it had 0 as its x-coordinate and 4 as its y-coordinate. Now the x-coordinate basically is how far to the right or to the left we go along the x-axis. If x equals 0, we don't go to the right or to the left. We stay on the y-axis. And y equals 4, that means we go 4 units straight up. From this point where the x and y axes intersect each other is called what? The 0 point for both of them? What do we call that point? The origin. We call it the origin. And sometimes it's easier to say the origin than it is to say the point 0, 0. That has way more syllables than simply the origin. Okay. The origin is not a solution to this equation, obviously, but it's an important reference point. 4, 2. If I want to plot the point 4, 2, I need the point that corresponds to x equals 4 and y equals 2. So you can think of it as starting at the origin and going 4 to the right and 2 up. Or just think of it as finding your way to the point 4, 2 and noticing that the x-coordinate below that, or the x value on the x-axis below that, is 4, and the y value to the left of that is 2. So there's the point 4, 2. And 8, 0, the point that had 0 for its x-coordinate was on the y-axis. Any point that has 0 for its y-coordinate is going to be on the x-axis. This one, 8 units to the right of the origin on the x-axis. That's where 8, 0 is. 6, 1, 6 to the right and 1 up puts us right there. 2, 3, starting at the origin, 2 to the right and 3 up puts us right there. So 5 out of the bunches and bunches of solutions to this equation. I want the picture of the entire solution set, not just these 5 solutions. So would it make sense to connect the dots? When I connect the dots, and if I extend it up to the left and down to the right, what will be the shape of the graph?
Line.
It will be a line. And so if I connect the dots and do it in such a way that I extend it infinitely far down to the right, I'll just draw the arrow. I can't draw it infinitely far, but I can draw the arrow indicating that's where it's going. And infinitely far up and to the left, call this straight line the graph of this equation. What I'm saying is really a couple things. I'm saying that every point on this graph represents an ordered pair that's a solution to this equation. So certainly these 5 are, but if we find any other points, carefully identify their coordinates, it means they have to satisfy the equation too. Going to do the midpoint formula in about 10-15 minutes or so. I haven't done it yet, but I think we could figure out, if we had to, the coordinates of a point that's halfway in between 2, 3 and 4, 2. Would you agree, first of all, I guess this is the important thing, that the point that's halfway in between these 2 points is actually on that line? Is that believable? I believe that point's on the line, for sure. What are the coordinates of the point that's halfway in between 2, 3 and 4, 2?
3 and 2 point something.
Looks like 3 and 2.5. We'll see this again when we do the midpoint formula. Would it make sense that the x-coordinate is halfway in between 2 and 4? I think so. That's 3. And would it make sense that the y-coordinate is halfway in between 2 and 3? 2.5 would be halfway between 2 and 3. So this point is on the graph. Does that ordered pair, 3, 2.5, satisfy the equation? 3 plus 2 times 2.5. 3 plus 5 equals 8. So it does. So what we're saying is that every point on this line satisfies the equation. What we're also saying is only the points on the line satisfy the equation. So if we pick a point over here somewhere, like that one, what's that, 10, 9? Would we expect this ordered pair to satisfy the equation?
No.
No, it's not on the line. So we certainly do not want it to satisfy the equation, or we have to include it with the graph. 10 plus 2 times 9. We're wondering if that equals 18. I'm thinking it's way too much. Sorry. If we're wondering if it's 8, I'm thinking that's way too much. it would be way too much even if I wanted to beat 18, which of course it doesn't. So 28 is not 8. So no, that point is not on the line, so that ordered pair is not expected to satisfy the equation. So when we draw the graph like that, what we have is a picture of the solution set. We can't list all the solutions, but we can draw a picture of the solution set. Key points on there, I mentioned this a moment ago. A point on the graph where the graph intersects the x-axis is called an x-intercept. 8, 0 is the x-intercept. Sometimes my math lab will just want the x-coordinate. If it says, what are the x-intercepts? It's just looking for the number 8. The y-intercept is the point 0, 4. If my math lab asks for the y-intercepts, it might just want the number 4 there. So rather than an ordered pair, just the y-coordinate of that point. One more thing before we leave this picture. The x and y axes partition the plane into 4 regions, upper right, upper left, lower right, lower left, called what? Quadrants. Quadrants. And we label them, we number them basically. Where's quadrant 1?
Upper right, I think.
Upper right, where everything's positive. The x's are positive, the y's are positive in quadrant 1. At some point, it had to be decided how to number the other ones. Whether to go clockwise, counterclockwise, or just maybe number the other 3 at random. It was decided to number them in a counterclockwise fashion. So quadrant 2 is in the upper left, where the x's are negative and the y's are positive. Quadrant 3 is in the lower left, where both coordinates are negative. And quadrant 4 is in the lower right, where the x's are positive and the y's are negative. Points on the axes, if x is 0 and it's on the y-axis, or if y is 0 and it's on the x-axis, are not strictly speaking in any of these quadrants, but we say it's on an axis. So 0, 4, if the question would be what quadrant or upon what axis does the point 0, 4 lie, you would simply say it's on the y-axis. You don't have to say, well, it's kind of in between these two quadrants. You just say it's on the y-axis, just like 8, 0 is on the x-axis. Okay, so as far as graphs, I think I've said about as much as I want to say about that. Working our way toward the distance formula, we'd like to be able to take any 2 points and write an expression to calculate the distance, straight line distance between those 2 points in the plane. And that's kind of the purpose of this example, to lead us toward the distance formula and the idea behind it. I'm trying to revise my notes this semester, and I may revise them a little bit after the fact. If you printed out the notes, I'm sure you would have been grateful if I had copied the grid that I had in example 1, like I'm going to copy it for myself. I will, let's see, it's not there. I need the clean copy of it from here. I found the grid to be useful, and in the near future, hopefully for future semesters of college algebra students, I will provide that. But sorry about it, I did not get that done for you in this case. So here's the grid, and the real point of this problem is to find the d part, the distance between the point -2, 1 and 10, 6. There's -2, 1, and there's 10, 6. Everything else is constructed with the idea of helping us find the distance between those 2 points. So let me draw the line segment. There it is. We want to know how far apart they are. Part A says, okay, we want to do that. Well, let's plot the point -2, 1. Let's plot the point 10, 6. And this other point that's going to help us. 10, 1. There's 10, 1 right there. Now 10, 1 is chosen. Wasn't just chosen at random. It's chosen so that it has the same x-coordinate as one of the points, and so it has the same y-coordinate as the other one of the points. It has the same x-coordinate, obviously, the point that's directly above it, and it has the same y-coordinate as the one that is directly over there. Right? So we have that point. And then it asks us some distances. Find the distance between -2, 1 and 10, 1. Now because 10, 1 was chosen so it has the same y-coordinate as -2, 1, it's really easy to find that distance. The distance between those 2 points is the same as the distance or the difference between the numbers negative 2 and 10 on the number line. So how far apart are those numbers?
12.
12 units. Now, as far as calculating it, there's various ways. We can kind of look at it and say, well, there's 10, there's 2 more, so it's 12. But as far as, in general, the formula for finding the distance between two numbers on the number line, we want to subtract. Is that how we do it? 10 minus negative 2. Subtract one from the other. We could get 12. If we do it in the wrong order, if we subtract the 10 from the negative 2, let's imagine we don't know what the numbers are, we're just substituting into a formula. It's possible we could do this in the wrong order. We might get negative 12. So when we write the distance between two numbers on the number line, we might miss the sign. So if we want the formula, it's the absolute value of the difference between the x coordinates. Take the absolute there, absolute value there, we get 12. Or if we do it in the reverse order, take the absolute value there, the absolute value of negative 12 is also 12. So that's the B part. The C part, how far apart are the points 10, 1 and 10, 6? Absolute value of 6 minus 1. Take the difference between their y coordinates since they're on the same vertical line. That's the absolute value of 5. And that's 5, or if we reverse it, 1 minus 6 is negative 5, but you take the absolute value, you still get 5. So 12 units there, 5 units there, and then what we really are interested in, the distance between negative 2, 1 and 10, 6. How does having the 12 and the 5 help us find the distance between negative 2, 1 and 10, 6?
Like rise over 1 or something.
Well, we will look at slope in the not too distant future, but this one, what's that theorem from geometry that you can find? The hypotenuse, yeah, Pythagorean theorem. That's the one that works for us in this case. If we say a equals 12 and b equals 5, and we don't know c, what's the formula for finding c?
B squared is C squared.
That's the one. C squared equals a squared plus b squared. Usually, I guess we have the c squared on the right, but since c is the unknown in this case, I'm going to put the c squared on the left. If we say c squared equals 12 squared plus 5 squared, then that's 144 plus 25, or 169. Now, from our work in section 1.4 with quadratic equations, we know this quadratic equation has two solutions. One positive and one negative. Do we care about the negative one in this case? No, because it's a distance, a positive distance between these 2 points. So although we could say plus or minus the square root of 169, c equals 13, is that what it is? 13 times 13 equals 169? Or c equals negative 13, we can scratch the negative 13. We know these points then are 13 units apart. So this is the distance. All right. So if anyone, maybe an algebra teacher somewhere down the road, asks us to find the distance between 2 points, one option is to draw this picture. Plot the 2 points and then come up with another point that has the same x coordinate of one and the same y coordinate as the other. And I don't know, you might have been thinking this, why didn't I just go with that point? I could have drawn the triangle using that point instead. I just didn't feel like it. I went with this other one instead. A couple of options there. Draw the picture, use the Pythagorean theorem, and we've got it. I had a friend, acquaintance, I guess, in my high school geometry class that refused to memorize this distance formula that we're about to look at. And whenever he had to find the distance between 2 points, he just did this. He drew the picture, he used the Pythagorean theorem, and it was all good. I guess he figured the number of times he was going to have to do that in his lifetime, it wasn't worth memorizing the distance formula. But we'll look at the distance formula nonetheless. Here goes. The idea here is we want to express the distance between 2 points in terms of the coordinates of those points. If we know the x and y coordinates of each of the points, this formula will do it for us. So if I can draw this freehand without the grid, imagine that we have a point x sub 1, y sub 1 there, and a point x sub 2, y sub 2 there, and another point that has the same x coordinate as that one, and the same y coordinate as that one. We can find the distance between these 2 points by constructing a right triangle, and then considering how we would calculate the lengths of those sides, the legs of the right triangle. This one is going to be the absolute value of the difference between the x coordinates. Just like we had 10 minus negative 2 in the previous example, x sub 2 minus x sub 1, and be sure to take the absolute value to make sure it's not negative. This one, the absolute value of the difference in the y coordinates, the 6 minus 1 that we had, or whatever that worked out to be, take the absolute value and that'll give that distance. If this is little a and this is little b, and I'm going to call this, well, I'm just going to put d for distance there. What we can say is that c squared equals a squared plus b squared. That's our formula for the Pythagorean theorem. But if I'm going to call the length of the hypotenuse d for distance, then what I'm saying is d squared equals x sub 2 minus x sub 1, absolute value of that, quantity squared, plus y sub 2 minus y sub 1, absolute value of that, quantity squared.
How do you get the absolute values of A and B on the legs? I don't understand. Oh, I see the x sub 1 and y sub 1, and I see the x sub 2 and y sub 1. Why is the absolute value x sub 2 minus x sub 1?
It's just to make sure that when I call this the distance between these 2 points, if I say the distance is x sub 2 minus x sub 1, there's situations where x sub 2 might be less and x sub 1 could be greater, and I'm actually telling you the distance is a negative number. And I only put the absolute value there just to make sure that if I've got it mixed up, it'll come out to be a positive number rather than a negative number. That's the only reason there. And we'll see in a moment that the absolute values for the distance formula turn out not to be absolutely necessary. In the final answer here, we've got just plain old parentheses. So for some reason we don't need them. Let's see why. If I take the square root, it would look like this. Just the positive square root of absolute value of x sub 2 minus x sub 1 squared plus absolute value of y sub 2 minus y sub 1 squared. This would work for the distance formula, but someone observed at some point, we really don't need those absolute value bars. I hope we can see why we need them here. Why do we not need them in the distance formula? Why are they just kind of overkill?
It's got to be positive.
Well, x sub 2 minus x sub 1, if we don't take the absolute value and square it, we get an answer. If we do take the absolute value and square it, we get the same answer. Whether we take the absolute value or not, if we're going to square it, then we're going to get the same square. So it turns out that we just don't need, after all that discussion about absolute value, we just don't need the absolute value in the final version of the distance formula just like that. So that's what it looks like. So if we want to find the distance between 2 points, without drawing the picture, without drawing the right triangle, finding the additional point, and using the Pythagorean theorem, this does it for us. It does everything that the Pythagorean theorem does. It just it streamlines it a little bit so that it's not necessary to have to draw the picture. So the distance formula example is here. I think I want to grab another copy of that grid. There is the example. And back to the top. Not that top. That top, sorry. The grid is very, very helpful. There. Okay, so I derived the distance formula so we don't have to draw the picture. I'm going to draw the picture anyway. Let me at least set up the distance formula. That's x sub 1, and that's y sub 1. That's x sub 2, and that's y sub 2. Now, it turns out not to matter which one we call x sub 1, y sub 1, and which one we call x sub 2, y sub 2. Either way is fine. 10, 1 is right there, and 2, negative 5 is right there. So I'm going to connect the dots, and what we're actually trying to find is the length of this line segment, the distance between those 2 points. Let's try it first real quickly, I think, with the picture without the distance formula. Just without the distance formula, if I draw this leg of the right triangle and this leg of the right triangle, how far is it from there to there? Length of that horizontal line segment, how far apart are those 2 points?
8.
8 units. And then how far is it from there down to there?
6.
6 units. So if we want to go directly to the Pythagorean theorem, c squared equals 8 squared plus 6 squared. C squared equals 64 plus 36. C squared equals 100. What positive number can you square and get 100? 10. So equals 10. So there. With the picture, I don't know, that might have been faster than using the distance formula. Let's see what the distance formula looks like, and let's compare. D equals the square root of. All right, do we need the distance formula for reference? Possibly. X sub 2 minus x sub 1 quantity squared plus y sub 2 minus y sub 1 quantity squared. There it is. So it's going to be the difference in the x's, 2 minus 10, and square that. Then the difference in the y's. Negative 5 minus 1, and square that. D equals the square root of the square of negative 8 plus the square of negative 6 Now, although we had a positive 8 and a positive 6 when using the Pythagorean theorem, we happen on negative values here, but when we square them, we still have the 64 and the 36. They were key players when we used the Pythagorean theorem, and likewise in the distance formula, d equals the square root of 100, and again we get 10. So I think the connection between the distance formula and the Pythagorean theorem is important. In practice, no need to draw the picture, just apply the distance formula and it should be fine. Midpoint formula. If we have 2 points in the plane, a little while ago, it was helpful to us to find the coordinates of a point that was halfway in between 2 other points. Midpoint formula kind of gives us a streamlined process whereby we can do that. If we know the coordinates of the endpoints, we can find a point that's halfway in between. And yes, I'm going to go in with another copy of the grid because it just helps. A special case, there'll be a different case in the actual example, but in looking at the midpoint formula, I need a couple points. I think I'm going to keep in the first quadrant. Let's go with this point, and then over here, up to there, maybe just here. These 2 points. And we're looking for the coordinates of the point that's halfway in between them. Let's see how we'd go about getting that. I'm going to go ahead and label them. This looks like 8, 7, and this one looks like 2, 3. Now, what I want you to believe, without having to show you a sophisticated geometric proof of similar triangles or anything like that, is that the x-coordinate of the point that's halfway between these 2 points is the number that's halfway in between the x-coordinates of these 2 points. Say if this x-coordinate is 2 and this x-coordinate is 8, what number is halfway between 2 and 8? That's trickier actually than it seems. Would you believe 5? Would you believe 5
Yes.
is halfway between 2 and 8?
Yes.
It's 3 less than 8, it's 3 more than 2. One nice way to calculate the 5 is to find the average of 2 and 8. The average. If you have a whole bunch of numbers, how do you find the average of all those numbers? What's the rule? Yeah. Add them together, divide by however many there are. If you want to find the average of two numbers, you add them together
Divide by 2.
and divide by 2, just like that. So we get a 2 and 8, add them together, get 10, and divide that by 2, and get 5. So 5 is the average, the numerical mean, we call it, of 2 and 8. So 5. What number is halfway in between? This is curious. Halfway between 2 and 7. Didn't mean for it to happen this way. But is, sorry, not 2 and 7, 3 and 7. 3 there, 7 there. Halfway between 3 and 7 is going to be
5.
5. Yes, that was unfortunate that it worked out that way, but maybe fortunate. Add the 3 and 7 together, get 10. And half of 10 is, 10 divided by 2, is 5. So it would appear that the coordinates of the midpoint are 5, 5. That's it. But in each case, we take the coordinates of the endpoints, add them together, divide by 2, and that gives the coordinates. And that's the formula. X sub 1 plus x sub 2, divide that by 2. Y sub 1 plus y sub 2, divide that by 2. So for a specific example, let me go with the grid yet again. And let's see, first I want to find, oh good, let's do the grid first. Right there. And then the specific example, right about there I guess. Hope that's not making you dizzy. I think that's the last time I'm going to have to do that today. There, just got the corner off of it. That should be okay. Find the midpoint of the line segment whose endpoints are 10, 1, and 2, negative 5. We dealt with these points a little bit ago. 10, 1 is right there. 2, negative 5 is right there. Let's use the midpoint formula, and then we'll connect the dots, find the point halfway in between, or plot the point that the answer we get, and see if it looks like it's halfway in between. So again, I'm going to call this one x sub 1, again y sub 1, again x sub 2, again y sub 2. So using the midpoint formula, just for reference here, I'll put it, we average the x coordinates, 10 plus 2, add them together and divide by 2. We average the y coordinates, 1 plus negative 5, add those together and divide by 2. This looks like 12 over 2. This looks like negative 4 over 2. So what number is halfway between 10 and 2? I guess it's not obvious that that's 6, is it? 6 is halfway between 10 and 2. It's kind of 4 units away from either one of them. And halfway between 1 and negative 5 is negative 2. Negative 2 is 3 units away from 1 and 3 units away from negative 5. So does it look like, be careful how I draw it, I kind of like it to go through that point. Does it look like 6, negative 2 is the midpoint? Yes. Sometimes this problem is missed because I'll see students use minuses in the midpoint formula. I would guess because the formula is learned in such close proximity to the distance formula that has minuses in between the coordinates. But if you understand and think of it as the average of the x coordinates, the average of the y coordinates, what's halfway in between them, then should be no reason for minuses. I think it'll make more sense. In the remaining time, let's see what we can say about symmetry. Symmetry from section 2.2. Some beginning thoughts about symmetry in general, 2 basic types of symmetry, and then we'll try to apply that to the x-axis, the y-axis, and the origin. So 2.2, we will get to this picture in just a moment. Beginning with 2.2, graphs of equations. First of all, 2 basic types of symmetry. let me do something like this. Symmetry with respect to a line and symmetry with respect to a point. Okay, the picture where they're basically two halves and they're mirror images of each other about some straight line would be symmetry with respect to a line. Another case where it's a little different, where there's a point that's kind of in the middle, and anything around the perimeter of that, there's something to balance it on the other side. Something all the way around this point, something to balance it on the other side. Loosely, that's kind of what we mean. A little bit more rigorously, the lines that we're eventually going to be interested in are either horizontal or vertical, the x-axis and the y-axis. But let's define this with a slanted line. Something maybe like this. And I'm just going to draw kind of a random graph consisting of some connected points, so line segments connecting some points, and see if we can reflect it about this line so that we result in a graph that's symmetric with respect to this line. So first, some bright blue points. Maybe a point there, and a point up there, a point across there somewhere, and something up there. And I connect these points with line segments like that, and like that, and that. This could be done if the graph had curvature to it, but it's simpler if we just have line segments. Now I have to be careful in finding the images of these points. The picture that you see on the screen has a different aspect ratio. Goodness, I'm so sorry. Has a different aspect ratio than what I'm seeing on my screen, so I'm kind of going to have to look up the screen. Anybody watching this video after the fact, it's really not going to look like the symmetry that it should, but that's fine. It's more important for you all than it is for the video watchers. So let's see. No offense, video watchers, but I want to make sure I get this right at least once. What I want to do is start at this point and find the image of this point about the straight line. So what I have to do is go toward the line and out the other distance, going straight to the line, and plot a point that's the same distance, same distance away from that line, and then connect the dots in such a way that this point right here is the midpoint of that line segment. Looks like I went maybe a little bit too far, but I won't be too hard on myself. And that this is a perpendicular line. It's perpendicular to the line segment. So that's kind of what that would look like. And I need to do this with each of the 4 points. So I want to go directly, and I can kind of use parallel lines to do this, directly toward the line in a perpendicular kind of way, and out the other side the same distance, and that's the image of that point. Doing it with this point, I have to go toward the line the other way, so directly toward the line, out the other side about the same distance. I think that's almost got it. And then with this one, it's not too far from the line, but directly toward the line, out the other side, the same distance, and plot a point. So these 4 points are the images of the 4 points that I had. I want to connect those dots in the same order that I connected the first 4, the 4 blue points. And what will happen is that will be the reflection of the line segments when I do that. So let's go with this and that and that. And what I really should do is take and erase these kind of guidelines that I drew in order to find the images of those points, because those really, they look like they're part of the graph because of the same color as what I did there, but they're really not officially part of the graph. That's the result. And if I take the red graph together with the blue graph, the union of those 2 graphs is going to be symmetric with respect to this straight line. If we were to take this on paper and fold it along the straight line, then the two sides of this would correspond to each other. The images would correspond to each other. So this is a graph that is symmetric with respect to that line. Symmetry with the point is a little bit different. type thing. So I'm going to put a point here, a purple point. Here's a purple point right there. And I want that to be the central focus of this picture. Now, I'm going to construct a line. I kicked myself right after I did this in the 8 o'clock hour. I said I should have just, after I'd done the blue graph, just copied it and pasted it over here, but I didn't, and I didn't do it again. But I think I can roughly copy that. So maybe something like this, a point there, and a point up like that, and a point down there somewhere, and then another one up here. That's roughly what the blue graph looked like. Connect the dots, straight line segments. And it looks like this. Now, as it stands, this graph is not symmetric with respect to that point. If you want to try to find what's in the middle of this picture, you would not go to the purple point and say that's in the middle. It's just not. But if I want to adjust this graph in such a way, I'm going to have an issue with this, and I want it to be as clear as possible. I just noticed something that's not going to work out as nicely. Well, that was weird. Huh, okay. I don't want to have to, as I'm finding images of these points, I don't want to go from one point and have to go through a different point, so I just scooted the purple point a little bit. Hopefully it won't affect the final result. For each of these blue points, I want to find the image of that blue point on the other side of the purple point. So let's go with red again. Starting with this one, march directly toward the purple point, out the other side the same distance, like that, and plot a red point. We'll say the red point and the blue point are images of each other about the purple point in the middle. All right, from this blue point down to the purple point and out the other side the same distance. There we go. We find a red point, so those points are images of each other. From this blue point directly toward the purple point, out the other side the same distance. Those points are images of each other. One more. This blue point, oh wow, am I going to fit it on the screen? Maybe. Straight down there. I wasn't thinking that when I scooted the purple point down. As far as I can go, maybe down there. So that almost gets it on the screen. Now, when I connect the red points in the same order that I connected the blue points, and let's see if I can do this. This was the first one, and this was connected to this one, and this one went across like that, and finally down like that. There we go. The resulting picture should be symmetric with respect to the purple point. That should be the central focus of the diagram. And now if we pick any point at all on either any of the blue line segments or any of the orange line segments, say a point right there, if we march directly toward the purple point out the other side the same distance, that point, the image of that point, should be on the graph. If we pick this one and go to the purple point out the other side, its image should be on the graph. So we'll say this graph is symmetric with respect to this point. All right, that's kind of the general idea, what we mean by symmetry with respect to a line, symmetry with respect to a point. Let's apply this, the x-axis to the y-axis, and to the origin. So we have this picture of a graph which is intended to be, and I believe is, symmetric with respect to the x-axis. Now the x-axis extends out like this, y-axis goes up like that. Let's look at the definition of symmetry with respect to the x-axis and see if this makes sense. A graph is symmetric with respect to the x-axis if for every point, and I'll plot this one for reference, but we could do this with any point on the graph, for every point xy on the graph, the image of that point about the x-axis is also on the graph, and if the original point is xy, its image would be given with what coordinates? How could we express the coordinates of that image in terms of x and y? Yes, same x coordinate, opposite y coordinate, just like that. Same x, opposite y. So if xy is on there, x negative y is also on there. And we'll see a test for symmetry, yes, I think in a few minutes, where we'll be able to substitute negative y for y in the equation and see if the graph of an equation has x-axis symmetry. And then there's y-axis symmetry. Picture looks something like this. Could look something like this. A graph is symmetric with respect to the y-axis if for every point, and here's a reference point, x, y on the graph, the image of that point, negative x, y. Oops, I'm sorry, I was supposed to pause and ask you to produce that ordered pair for me, but does it look like it ought to be true?
Yes.
Opposite x coordinate, same y coordinate because we're going straight across. The image, negative xy, is also on the graph. So this is a visual where the y-axis cuts it right down the middle. You could fold the two sides of the graph along the y-axis, and they would coincide with each other. And back to that test for symmetry in a moment. But origin symmetry, a different kind of vibe, I think, since it involves a single point, symmetry about a point, rather than symmetry about a straight line. A graph is symmetric with respect to the origin if, for any point x, y on that line, on the graph, its image, what is the image of x, y with respect to the origin?
Negative x, negative y.
Negative x, negative y. Both of them have to be opposites because it's on the other side of the y-axis. It's on the other side of the x-axis. So negative x, negative y is going to be the image of that point with respect to the origin. This would be an example of a graph that has origin symmetry. Now, a couple things we want to be able to do. Given a picture, someone gives us a graph of an equation, maybe later a function, we'd like to be able to look at it and classify if it has one or more of these three types of symmetry. We want to put it in that category, call attention to it, because there's some useful information that we can get from knowing that a particular graph has y-axis symmetry or a particular graph has x-axis symmetry. We don't do trigonometry in this class, so nobody worry that I'm going to pull out some sines, cosines, tangents, none of that. But the 6 basic trig functions, sine, cosine, tangent, cotangent, secant, cosecant, all 6 of them have at least one of these 3 types of symmetry. In fact, none of them has x-axis symmetry. All of them either have y-axis symmetry or origin symmetry. And it turns out to be useful in the study of trigonometric functions to know what types of symmetry that they have. So if a function has one of these types of symmetry, we want to call attention to it and be aware of it. So looking at the picture, we want to be able to recognize that. But also, looking at an equation, no picture in sight, have no idea what the graph might look like. We want to be able to determine, just by a substitution and simplification, whether the graph is going to have one of these 3 types of symmetry. It can be helpful if we need to sketch the graph. We can cut down on the amount of labor that might require by recognizing what type of symmetry it has, but it's helpful before the fact to know what type of symmetry it's going to have. So there are tests for symmetry, x-axis, y-axis, and origin symmetry that we want to be able to apply to an equation even if we don't know what the graph looks like. The test for x-axis symmetry, if xy is on the graph, then x negative y is going to be on the graph. So if xy satisfies the equation, x negative y must also satisfy the equation. What we can do in our equation, if we suspect that its graph may have x-axis symmetry, is substitute x for x and negative y for y, and if we can make it look like the original equation, then we've shown that it actually does have x-axis symmetry. Now, substituting x for x really doesn't change anything, so we don't emphasize that, but what we do emphasize is that we want to replace y by negative y. Likewise for y-axis, because negative xy satisfies the equation whenever xy does, we'll substitute negative x for x, simplify, see if we can make the equation look like the original. For origin symmetry, if we suspect that the graph may have origin symmetry, we'll do both at the same time. Substitute negative x for x and substitute negative y for y. Simplify both sides of our equation, see if we can make it look like the original. Now, in the process of doing this, we do want to keep in mind that there are only 5 cases, for these three types of symmetry. Except for the fact that I would want you to show your work, it actually makes for a pretty good multiple choice question. Which of these three types of symmetry does the following graph have? Great question, because the possible choices would be these. X-axis symmetry only. It's possible for a graph to have x-axis symmetry, neither y nor origin. And a big time case in point is this one. This graph has x-axis symmetry. You can fold it about the x-axis. Does this graph have y-axis symmetry? No, because you've got xy, but you're missing the image of xy, negative xy. So it doesn't have y-axis symmetry. Does this graph have origin symmetry? No, because even though we have xy, we're missing the image negative x, negative y about the origin. So x-axis symmetry only. 2. A graph may have y-axis symmetry only. That is, have y-axis symmetry, but not x-axis symmetry or origin symmetry. And that picture is right there. This graph has y-axis symmetry. Does it have x-axis symmetry?
No.
No. Take this point. The image is nothing down there. So you can't reflect it about the, if you reflect about the y-axis, you get points that aren't there. And does it have origin symmetry? No, xy does not have its image there about the origin. So y-axis symmetry only. 3. Origin symmetry only. It's possible for a graph to have origin symmetry without having either x or y-axis symmetry. And I think this is such a case. Does this graph have x-axis symmetry? If we march directly across the x-axis, we're missing the image of that point. Does it have y-axis symmetry?
No.
No. If we march directly across the y-axis, we're missing that point. So it doesn't have x-axis, doesn't have y-axis. Origin symmetry only. Is it possible for a graph to have more than one of these three types of symmetry? It is possible. Suppose we have an existing graph and we want to give it more symmetry without losing the existing symmetry. Suppose we have this picture and we want to give it, what should we add to this? Maybe
Fill in the rest of the triangle.
fill in the rest of it. So let's add, you want to add x-axis or y-axis to it? Let's add...
Both?
Yeah, it turns out, that's the punchline. It turns out we can't do one without the other. But let's do this with the intention of adding x-axis symmetry. If we want to add x-axis symmetry, of course, we have to take what's in the first quadrant, reflected about the x-axis, and we get this, right? But wait, there's some points, line segments down here in the third quadrant that also have to be reflected about the x-axis, and when we do that, we would get this. Does the graph still have origin symmetry? That's important. I don't want to lose the origin symmetry. That's okay. Have we successfully added x-axis symmetry to it so you can reflect about the x-axis? But without perhaps intending to, have I also given it y-axis symmetry? It turns out, there's a proof for this, but time is short. It turns out that if a graph has one type of symmetry and you add a second to it without losing the first, you automatically get the third one for free. It's not possible for a graph to have exactly two of these three types of symmetry. So x-axis only, y-axis only, origin only. All of the above, we just saw that. This picture now has all of the above. It has all three types of symmetry. And what's the fifth possibility?
None?
None of the above. Yeah. None of the above. Just draw random squigglies, and chances are it will have none of these three types of symmetry. We'll begin with that example 1 next time and actually test these equations and see which ones have graphs that have symmetry and which ones have graphs without symmetry? If so, which types of symmetry?